Okay, thank you, Claude, for introducing. I will just... Okay, this is starting. Okay, thank you for coming to this seminar. So the main topic of the seminar is volcanoseismology, but I'm not pretending in this talk to give you some exhaustive overview of this field. This will be just impossible because this is an old, very rich, very complex field of study. And also, I myself, I'm not, strictly speaking, volcanoseismologist. There are many details about volcanoseismology that I simply ignore. So what I will rather show you is my personal view of some problems. Oh, yeah. Okay. Of some, I'm sorry. I will show you my personal view of volcanoseismology and of some first-order outstanding problems that, in my view, still remain unsolved. And this is why I consider this field being one of most exciting parts of seismology in general. Okay, so here's the approximate plan of my presentation. So I will start with comparing volcanic earthquakes with ordinary tectonic earthquakes. Then I will briefly speak about how seismology is used in volcano monitoring. Then I will not show too many examples. I will show one example of study from Kamchatka. Then I will discuss some similarity between volcanic and tectonic seismicity. And at the end, I will present you some ideas about how I think the volcanoseismology should evolve to advance to be able to solve these unsolved outstanding problems. Okay. So I start with comparing regular earthquakes and volcanic earthquakes. Regular tectonic earthquakes are earthquakes that occur on tectonic faults that are reported every day by earthquake monitoring agency, and volcanic earthquakes are earthquakes occurring within volcanoes. And there are many important differences between these earthquakes. But to start, I think both of these types of earthquakes were observed very early when seismology started. So these two types of seismicity has been studied for more than 1 century now. So one major difference between tectonic earthquakes and volcanic earthquakes is their size. Tectonic earthquakes may be very large, destructive, and so on. Most of volcanic earthquakes are very, very small and almost never felt at the surface. Then what is important is the amount of earthquakes. Contrary to what one could think, there are more volcanic earthquakes that occur than tectonic earthquakes, and I will show this. And then very important issue is our understanding of the source process. For tectonic earthquakes, we have some clear paradigm of the source model and interpretation, and this is something that is missing for volcanic earthquakes, and I will discuss this in more detail. So first of all, about the amount of earthquakes. So actually, they're difficult to compare because we have very complete catalogs for tectonic earthquakes and much less complete catalogs for volcanic earthquakes, but we can just take some examples. For example, seismicity in France. In metropolitan France, if we take official catalog from this publication, I don't have, from a publication, so the last year when I could find the data is 2009, and there's on average 5 earthquakes per day. We could think that there are more earthquakes reported in Antilles subduction zone, but actually from their catalog we have approximately the same number. Now, if we try to compare this with the French volcano, Piton de la Fournaise, those are few examples. Again, I could not find a complete catalog. It is not easily accessible, but this is just an example from one of the latest observatory reports a few months ago. For example, there was one day there was seismic crisis with this amount of earthquake, and then in this publication, these authors studied period preceding this eruption, and they found during almost 2 weeks consistently more than 1,000 earthquakes per day. You see, if we consider France, actually the most of earthquakes that are generated by this relatively small object, Piton de la Fournaise volcano. Obviously, France is not the most seismically active area, so we can compare this with other areas. For example, a very active subduction zone, Kamchatka Peninsula, And so that is monitored by seismic network that is shown here with triangle, different types of seismic stations. What I want to show here is just basic statistics from the official catalog of Russian Geophysical Survey. So for this area, based on the same monitoring methods and same network, they report on average 20 tectonic earthquakes per day and 90 volcanic earthquakes per day. You see there are much more volcanic earthquakes than tectonic earthquakes again. And then if we think globally, how many volcanoes are in the world, how many of them are active. Here there are some numbers. We don't know exact number of active volcanoes, but geologists estimate that there are about 1,500 volcanoes that are considered as active or potentially active, implying that they were at least once active during Holocene. And among these volcanoes, at least 50 erupt every year. So this implies that there are a lot of volcanic activity constantly on the S, and this implies that we can observe very huge amounts of volcanic earthquakes. So if this implies if we want to do some statistical study of earthquakes, if we want to find huge catalogs, volcanoes are the best source for this on the S. And this is not surprising because volcanoes are obviously very dynamic with a lot of strong forcing from stresses and fluid pressure. So now let us discuss the complexity of the source model of tectonic earthquakes and volcanic earthquakes. First, I will briefly describe the existing paradigm for interpretation of tectonic earthquakes. So I think everybody knows the basic idea of tectonic earthquakes, that they are produced by sudden release of shear stress on break and rupture. So essentially we have elastic media that is deformed under tectonic stresses. This leads to accumulation of shear stress in some area along some fault plane, and then suddenly this fault breaks, and this is what we call earthquake. So this is a conceptually very simple model, and it has also a very simple and straightforward mathematical description. Actually, this kind of seismic source can be described mathematically with moment tensor, with the deviatoric part equal to 0, and this is what is often represented on tectonic maps with this beach ball representation. I will not go into detail of this. And then we can introduce a very simple dynamic parameter describing the size of the earthquake, which is seismic moment, which is essentially the product of the faults area on the slip and on the shear modulus. Okay, so this is a really very simple and efficient mathematical description. And then what is important also for tectonic earthquakes is the existence of simple scaling laws between main earthquake parameters such as seismic moment, source duration, source size, and so on, for example. And this has been established already many years ago by these authors. There are two, I would say, keystone papers on this subject from Katie Aki and Hiro Kanamori, when they show that very simple mathematical model can explain the scaling between main parameters of earthquake, like magnitude and size in this case, or others, for earthquakes in the range of magnitude between, I would say, 2 and 9. Okay, so this is something very powerful, because with this simple mathematical description and scaling law, we can have simple physical interpretation for the earthquake magnitude. So this allows us to introduce moment magnitude scale. So the earthquake magnitude is simply related to seismic moment. And essentially this implies that once we measure a magnitude, which is a rather simple measurement, we can have a good approximation of the size of earthquake, which is shown here. So for a very large earthquake, the size of the rupture is of the order of thousands of kilometers, and the slip is of the order of tens of meters, while for the small earthquakes, the rupture size is very small, and also the slip decreases proportionally. Okay, so essentially we have this very nice and simple model that describes ensemble of tectonic earthquakes. Obviously, all this is valid rather in a statistical sense. For every individual earthquake, we may have deviations, but this simple rupture model and scaling laws allows simple interpretation of earthquake observation. This is why we can use earthquake observations or seismograms of earthquakes for quantitative interpretation in terms of tectonic process and other things. So essentially we have our forward problem that relates the rupture parameters through seismic moment. We can predict seismograms, and then based on this we can formulate our inverse problem where we use these seismograms to inverse for source parameters such as magnitude, seismic moment, focal mechanism, or rupture plane orientation, and so on. And based on this we can have these quantitative parameters and use them for quantitative interpretation in terms of fault properties, mechanical stresses, seismic coupling, seismic hazard, and plate tectonics. Okay, so we have very nice paradigm for understanding and using these earthquakes. Okay, now what about volcanic earthquakes? As I already announced initially, the situation is much more complex. I cannot explain it or illustrate it simply what I selected. For this, I just took this relatively recent review paper from Bernard Chouette, who is one of the major figures in volcano seismology, and just show you its content. You see there are many points, so many different types of, two main types of seismicity, many possible types of mechanisms. So essentially, if we will read through these or other review papers about volcano seismology, you will not find one simple model. You will find a multiplicity of models or scenarios rather than models that have been validated sometimes in some particular case, but no universal paradigm for interpretation of observations. Okay, so this is what the major difference between earthquakes, tectonic earthquake seismology and volcano seismology. Okay. So there are obviously reasons for this. So the reasons for this are in the complexity of a volcanic system. So here I show you some cartoons that illustrate what we believe about the functioning of volcanoes. Okay, so essentially what is from different geological, geodynamic, and so on data. This is believed that volcanic melts are originated somewhere in uppermost mantle, then they rise to the crust mantle boundary, form intermediate magmatic reservoirs at different level, and then when they propagate from the bottom of the crust to the surface, there are different chemical processes, especially degassing, that occur, and all this is very dynamic and so on. So essentially, if we want to describe the physics and dynamics of the system, we need many physical components: solid deformation theory, fluid dynamics, poroelasticity, physical chemistry of minerals, rocks and gases, and so on. Okay, so this is very complex, and we obviously expect complexity in such system. Okay, I will go through this. And this complexity is obviously observed in volcanoes. The best illustration is the huge variability in the style of volcanic eruptions. Here I just show you two extreme examples of volcano Tolbachik in Kamchatka with Hawaiian style of eruption, when magma is flowing quietly, and very explosive eruption of Bezymyany volcano in Kamchatka, and the difference main origin in this difference is type of magmas and their viscosity. And what is interesting to note, the distance between these volcanoes are just 50 kilometers. Okay, they're very close to each other. Okay, so we all know that volcanic systems are complex. Okay, we also observe the same level of complexity in seismo-volcanic signals. This is just one very simple illustration of this complexity from this textbook by Japanese authors that showed different types of volcanic earthquakes. So there are high-frequency earthquakes, low-frequency earthquakes, explosions, tremors that are long-duration signals. And this actually is simplified representation of this. If we try to put different types of strange volcanic signals, this will be a separate presentation. Okay, but so basically one of the important things in volcanoseismology is classification of the signals, which is again a complex problem, but there is a first order classification in two types of seismicity. So first of all, these high frequency seismograms correspond to what is believed volcano-tectonic earthquakes that are believed to be caused by faulting or rupturing of small faults within volcanic edifice under stresses. So they're somehow similar to tectonic earthquakes. And then all other type of seismicity can be classified roughly as low frequency seismicity. Okay, you can see the difference in frequency content. And again, this is believed that this seismicity is mainly caused by process directly in volcano plumbing system related to some magma transport, fluid pressure perturbation, and so on. Okay. So now let us briefly discuss how seismology is used in volcano monitoring. Okay. So this is again some cartoon of a volcano. And volcano monitoring is a difficult, and generally studying volcano is difficult because main processes leading to volcanism occur at depths of a few up to 100 kilometers. But we cannot obviously observe them directly. We only have observations at the surface. Okay, actually most of information or knowledge we have today about volcano comes from geological study, very scrupulous study of volcanic rocks erupted, exhumed, petrology, geochemistry, geomorphology, and so on. Okay, but if we want to monitor volcano, we need to get some knowledge about the processes that occur today. And geology gives us knowledge about what happened in the past. So this is why we need different type of instrumental observations, like visual observation, measuring gas emissions, and then today also satellite observations are very widely used, and then geodetic and seismic observations. So one of the main methods of volcano monitoring is installing instruments like seismometers close to volcano, and actually seismic method remains, I would say, one of the main, if not the main method of volcano monitoring for two reasons. First of all, seismic waves are the most direct source of information from depths. So if something occurs from depths and emits seismic waves, we can record this and try to get some inferences about this. And then many other methods, they are very dependent on weather conditions. So if there is a bad weather, we cannot have visual observations, we cannot have satellite images. Also gas plumes can go away. So the most stable and robust method of observation is seismic and geodetic. Okay, so how seismic methods are used in volcano monitoring? Today, I would say in all volcano observatories, what is implemented is empirical approach. It consists in detecting different types of seismic signals, volcanic earthquakes and tremors, then classifying them in different groups, counting different types of events, locating them if possible, and then establishing some empirical relation between this type of activity and probability of eruption to occur. Okay, I call this empirical because in almost never in this interpretation there is some physical inferences about physical parameters at depth. I'll just show you some examples. For example, from Piton de la Fournaise, I think this was in February, this was the most latest eruption in it. And so this is a short extract of report of EPF. And so what they just tried, that they observe from the day before the eruption, 2 days before the eruption, they have seen some seismic crisis. Then it was decreasing, but the inflation was continuing. So they empirically relate this observation with this interpretation. So they think that magmatic reservoir continues to be realimentated from the depths, but there is no propagation of the magma to the surface. So again, this is a correct interpretation, but empirical. So there is no inversion, quantitative relation between seismic parameters and other parameters. On the next day, so they, first of all, they detect new seismic crisis and they interpret it as a possible propagation of the magma from the reservoir to the surface, and they say that eruption is very probable, and then at some point they detect volcanic tremor that they empirically know is equivalent to ongoing eruption. So, okay, they detected the preparation of eruption actually a few days before the eruption, and then they very clearly detected the onset of the eruption. So it works. So this is a very powerful but empirical approach. So if I speak about this empirical approach, it has very clear advantages. It's very simple to implement because it doesn't need any complex modeling for interpretation. So when it works, it's robust, but there are also many disadvantages. So empirical description obtained on one volcano is rarely transportable to another volcano. So also many volcanoes doesn't have a rich history of recent activity and instrumental observations, and for such volcanoes this is difficult to develop good empirical interpretation. And then we still miss physical understanding of processes and depths, and this is obviously, at least for me as a scientist, this is something that is very important. Okay, so then again, if we think about amount of volcanoes in the world, 1,500, so this is unenvisionable to develop exact empirical description of every volcano. So if we want to have more general volcanic monitoring, we need some different approach. Another example, so a volcano without recent eruptive history and instrumental observations. So Soufrière de Guadeloupe, again, a volcano monitored by IPGP. So this is one of the most recent report that I found in our IPGP email. And if you read it, it is just very descriptive. Essentially, there is a report that there was a sequence of 200 earthquakes, and this is all. Okay, so no interpretation in terms of what happens within the volcano. This is just because there is no past empirical information to relate this observation with knowledge about volcanic activity. So this is why this report remains very brief. Okay, so again, just not to criticize what happens on volcano observatories, but just to give you some idea. I think this is important to compare this with what is today reported for earthquakes, for monitoring of tectonic earthquakes. So, and this is an example again for a relatively recent earthquake here in Papua New Guinea. Okay, this is from United States Geophysical Survey, and they provide a lot of quantitative information, and in particular depths, moment tensor, magnitude, and this finite fault solution. Essentially, they show us this picture. They show that somewhere at the depths of more than 100 kilometers, there was such rupture with such amount of slip. So this is, you see, very direct quantitative information about rupture. So much more physically interesting information than in case of volcano monitoring. Okay, so here one of my main points about modern state of volcano seismology, that we still have major challenge in this field. We need to developing approaches that allows us to use seismo-volcanic observations to obtain direct physical information about physical processes in volcanic edifices, and especially in deeper part of plumbing systems. Okay, I don't have today answers how to do this. I'll just show you a few examples, or maybe one example. Okay, and I will focus on long period earthquakes and tremor, or long period volcanic seismicity that is believed to be related to the process in the volcano plugin system, so some fluid-related process, to magma and to other fluids. Essentially, if again we try to think about what happens in the volcano, again, this is not a real picture, this is a cartoon. So some volcanologists drew this to interpret his idea. So essentially we have some magma concentrated on the core mantle boundary, then it somehow rises through the lower crust, and at some point strong degassing starts. First of all CO2, then water is degassed, and we're close to the surface we have a very complex system with different fluids, with magma but also with gas bubbles and so on. So all this is very dynamic, it can generate seismic signals. Okay, and so what we would like is to take these seismic signals to detect these different sources and to try to figure out what happens in this complex system. Okay, so and now I show you one example from Kamchatka where we only very partially did some kind of this information, or we believe that we obtained some useful information. Okay, Kamchatka Peninsula, okay, this is northwestern Pacific, this very active subduction zone, and I focus on this Kluchevskoy volcanic group, my preferred place to study volcanoseismology and seismology in general, because this is a very active object. So this is the largest cluster of subduction volcanoes of the world. Overall, there are 13 huge volcanoes and many monovolcanoes, and then 3 of these volcanoes that are shown here are very active. Okay, and the magma production rate is actually very high, close to those of Hawaii, that is believed to be one of the most productive volcanic systems in the world. Okay, so this is what happens with seismicity on this volcanic group. This is the map. Essentially what this figure shows that these volcanoes generate a lot of seismicity. So this is for 10 years. Numbers just from regular catalog. You can see there are huge numbers of earthquakes. And then these earthquakes are mainly concentrated at 2 depths, very close to the surface, essentially inside volcanic edifices. And then there is this huge cluster of earthquakes at the core mantle boundary. And then I will just show you briefly that it turns out that most of these earthquakes are long period earthquakes. Okay? So, and in my study, or study I show you, we focused on this period from 2012 to 2013, oh sorry, from 2011 to 2012, because this was a preparation period of one of the major recent eruption in this volcanic system of this Telbacic volcano. This was eruption, again, this is a Hawaiian style eruption with nearly basaltic magmas, but important lava volumes. So this was a major event in this volcanic group. And so we tried to figure out what happened before this eruption. So this is the seismic network that we used. So triangles show position of permanent seismic stations. So, and here this volcanic group, Telbacic volcano is here, and other 2 active volcanoes are located here. So this is again Telbacic volcano, and this is an example of records of these long period earthquakes. So I will try to avoid all technical details about seismology. Essentially, there are a lot of them, and then they have this nice multiplet behavior. So when almost the same waveforms repeat many times, this actually makes their detection easy and very efficient. So we apply this template match detection. I stop here. It just allows us to detect at least 10 times more earthquakes than in regular catalogs, and sometimes even 100 times more. Okay, and so here's the result of this exercise. So it turns out that when we identified templates and detected all these long period earthquakes during 2 years, all their sources are located in very specific regions that are shown with these circles, actually beneath 3 main active volcanoes, Telbacic, Bezymyanny, and Kluchevskoy. And when we look at depths, there is a group of sources almost within volcanic edifices and 1 at the core mantle boundary. Okay, this is similar to what I already shown you, and essentially maybe we have 2 different types of processes. One is related to the shallow part of volcanic plumbing system with a lot of gases and so on, but another more interesting, this one in the core mantle boundary, where we have this deep long period seismicity that reflects the alimentation of volcanic system from the mantle. Oh, sorry. Okay, so again, so this is another way to represent these 4 groups of sources. So this is a cross-section across the volcano, 3 groups of sources near the surface, and this deep long period seismicity. And actually what we do for interpretation, very simple thing, we just count the number of earthquakes per day, which is shown here. So this is number of earthquake in this area for 2 years. Oh, okay, so this is 2011, this is the end of 2012, and this red arrow shows the onset of this eruption. And what we essentially see, if we smooth this gray curve in some like 100-day long window, we obtain this blue curve. We show approximate evolution of activity here at depths. We see that during these years preceding the eruption, the activity depth on average increases, okay, not steadily, it increases, decreases, increases, decreases, and then it reaches some maximum a few months before the eruption. And then when we see what happens at the surface, this is what is shown here, again, the same daily number of events for 3 sources, for Bezymyanny, Khrushchevskoy, and Telbachik, and the main is red curve for Telbachik because this is the volcano that erupted. We see that there is some clear delay between the maximum of activity at depths and the maximum of activity at the surface. Okay, and this is what we try to interpret in the following way. Essentially, we say that this is somehow related to propagation or diffusion of pressure through some imaginary volcanic conduit. Okay, so when everything is more or less non-active, as here, we have some pressure diffusive pulse rising from the deep mantle to the surface, and then when it reaches this crust mantle boundary, we have the maximum of activity at this level. Then it propagates further. So this is when the activity at depth starts to decrease, but activity close to the surface starts to increase, and it propagates further. At some point reaches the surface, and this is when the volcano erupts. Okay, so this is a very simple, but we believe plausible interpretation. And then what is interesting, if we use it, we can just measure the delay between this maxima and this maxima, and to estimate average propagation rate of this process, or rather to interpret this in terms of diffusion equation. In this case, we can estimate this value for the conduit that is an average coefficient of hydraulic diffusivity, okay, which is close to 100. Okay, so why it is interesting? Because then, based on this value, we can use some simple parameters and very simple interpretation in terms of porous flow, and to get an idea what is the structure of the imaginary conduit in the lower crust. And we get actually to make everything together, we need to have a conduit that is not just some tube, but rather some porous channel with these parameters that has 1 kilometer square in cross section, and the average pore radius is of the order of 1 centimeter. Okay, so this is again to get this interpretation, we obviously need to do many assumptions, but at least we end up with some quantitative inferences about this system. And further studies needed to verify if it's true or not. Okay, now, okay, I think I have maybe 15 more minutes. So I will speak about possible analogy between volcanic and tectonic low-frequency seismicity. Okay, so I go back to volcano monitoring, but now I will speak, so go back to earthquake monitoring, but now I'm considering it more broadly, not just monitoring of earthquakes as they occur, but what we want to monitor major faults and understand seismic cycle on these faults. Okay, and basic idea of seismic cycle is similar to what I've described before. So here it is illustrated for a subduction zone. So we have some locked zone that is charged with tectonic deformation, and at some point it ruptures, and then we have these possible scenarios of for the seismic cycles. So with trace accumulation that is interrupted by earthquakes. Okay, so if we want to monitor seismic cycle, what we would like to understand how long are these inter-earthquake periods, if they can be predicted or not predicted, or if we can observe something during these periods. Okay, in this purely elastic scenario, there is very few, essentially, not many things that we can tell about interseismic period because it is considered as quiet. Okay, but now with modern observations, again, seismological and geodetic, now we know that actually this interseismic period is not quiet. There are many things that are ongoing, and this is what I briefly will show you. So this is mainly related to this phenomena of slow earthquakes that has been discovered in the beginning of 21st century, more or less simultaneously in Cascadia in Japan. And it consists actually that the accumulation of deformation on this plate interface is not steady, but is rather intermittent with some accelerations, accumulation and acceleration and so on. So detected by GPS, okay? And also what is interesting during these so-called slow sleep events where the sleep on the fault plane accelerates, we observe low-frequency seismic signals, low-frequency seismic tremors and earthquakes, in some sense very similar to low-frequency volcanic seismicity. Okay, and initial study shown that all these slow sleep and low-frequency radiation originate on this down deep part of the fault zone. So we have elastically locked part of the fault zone with this tick slip behavior, and then beneath there is some transition zone that where all these slow earthquake occur. And obviously there is a mechanical interaction between these different parts of the fault, and the processes in down deep roots of the fault eventually can affect the seismic cycle. This is why they're very interesting. Okay, now let us think a little more about the faults. So this is the image that I just shown you. This is the interpretation of seismologist or geodetist. So essentially who consider the fault as a plane with sections with different mechanical or frictional properties. Locked zone, stable sliding, and some kind of transitional zone. Okay, but then if we ask geologists how fault zones are functioning, they will give us, I would say, different or even very different picture. So they consider faults not as a plane but as a fault zone with some internal structure. I'm sorry, I will not go into details of these figures, but what they show, those are figures from papers from Samuel and Jebust. And this figure shows that tectonic and geological modeling actually predicts that there are a lot of fluids within these fault zones, okay, that are released by different metamorphic reactions. Okay, and so this implies that things, the process that are occurring in these deep roots of the fault zones can be also related to presence of these fluids. Okay, and this is, in my view, creates some possible analogy between the deep roots of the fault zones and deep roots of the volcanoes. Okay, essentially, even if the geometry and stress orientation is different, we still have some system with some kind of channel that is forced simultaneously by stresses and fluid pressure. Okay, this is why this might be interesting to think about possible analogies about processes and seismic sources in these environments. Okay, and actually this is what people did when these slow earthquakes, especially the seismic component, low frequency or long period tremors and earthquakes were discovered. The first interpretation was in terms of fluid migration. And actually the first name of this observation was non-volcanic tremors. Essentially, this Japanese seismologist Obara-san, when he discovered this phenomena, he immediately think about analogy with volcanoes, and he just called it. This is not on volcanoes, but it's something very similar. And then when low-frequency earthquakes and fault zone were discovered, again, the two possible mechanisms were mentioned. Okay. So today, in the community study that study the slow earthquake phenomena, most of people don't think so much about fluids. They interpret these observations in terms of slow shear slip on the plate interface, whatever this means. But still, role of fluids is recognized as important, at least to increase the seismogenic behavior via increased pore pressure, but also the dynamic role of fluids in seismogenesis cannot be excluded. Okay, and here I just show you another example of our study very briefly. So in this case, we studied low-frequency earthquakes in Guerrero, Mexico. This is another subduction zone that is shown here. Okay. And what is interesting about this subduction zone is that the subduction is absolutely flat. So we have all this part of subduction and interface well exposed to the instruments installed on land. And we were lucky there was an experiment operating here. And also in this area there are very strong slow earthquakes. But what we studied, there were these low frequency earthquakes. Here I just show you example of a seismogram. Again, they were detected with the same template matched approach that I mentioned to you about volcanoes. I skip all details, I just show you results. So after doing very careful detection and so on, we detected almost 2 million earthquakes during 2.5 years. This equals to average of more than 2,000 earthquakes per day. Okay, huge amount of earthquake. And so this is the special distribution of these earthquakes. So they're located somehow close to subduction interface. But then if we look at the spatiotemporal distribution of this earthquake, sometimes we can identify migrations. Again, I skip the details, but what I just show you that sometimes we see the migration of seismicity in this direction, and with this speed, and again, if we try to interpret this in terms of diffusive system and porous channel, what is interesting, we end up with very close value of hydraulic diffusivity comparing to what we're observing for volcanoes. Okay, so I stop here. I just wanted to show you that there are possible similarities in analogy between low-frequency seismicity in volcanic systems and tectonic faults, that we may try to interpret them in terms of fluid processes, but all this is obviously remain to some degree speculative, and we need more observations to confirm or reject different hypotheses. In particular, all two cases that I shown you were based on very simple exercise. We just detected, located, counted earthquakes and considered their migration and interpreted the migration rate. We didn't do anything about magnitudes, moments, mechanisms, and so on. So there are a lot of things to do. Okay, so and now with this, I will speak 5 minutes more about what I think about what we should do to advance all these different things, especially volcanic seismology further. Okay, and I go back to this nice picture of the paradigm of interpretation of tectonic earthquakes. So this exists for tectonic earthquakes, and we would like to develop something similar for volcanic earthquakes and low frequency fluid relation seismicity in general. So, what's this? Sorry. Okay. Yeah. So essentially, we would like to develop some models when we have physical model of volcanic system. We can describe some seismic sources related with different process, predict waves, and then use this physical description to formulate inverse problem for volcanic seismic sources and inferences about different processes occurring in plumbing system, magma, pressure, rates, so on. But for this, we need this seismic source model that we basically don't have today. Okay, and this, I think, is the major challenge for volcanic seismology, but also for this slow earthquake seismology these days. Okay, so if we think about what we should do for better characterizing sources of volcanic earthquakes, the easiest, or probably easiest case is volcanic tectonic earthquakes that are believed to be similar to regular earthquakes, just smaller within volcanoes. If this is true, we can just implement the same tools that we use for regular earthquakes for volcano monitoring. Okay, and we can so do magnitudes, moment tensors, and so on. But actually, this hypothesis still needs to be carefully verified. For example, one thing that I didn't find clearly described in the literature are scaling laws for volcanic earthquakes, for volcanotectonic earthquakes. And without verifying the scaling laws, we cannot actually be sure if this analogy between tectonic and volcanotectonic earthquakes is real. So essentially, there's a lot of things to do to verify this basic scaling laws like Gutenberg-Richter or non-Gutenberg-Richter or magnitude duration scaling. Okay, then situation with long period volcanic seismicity is much more complex because today we don't have a simple conceptual idea about this. Essentially, we have a system of some channels with fluid flowing through these channels and interacting with elastic things outside. If we think what this can be a seismic source, these migrating fluids may open and close cracks or conduits. This will result in some kind of seismic moment tensor, but with strong non-deviatory component. But also, these moving fluids, they actually will exercise advection and viscous drag forces on the walls of the conduits or cracks or so on. And so we need to add a single force component to our source description, and how what component is dominant is a priori not clear. And then based on which component is dominant, we might develop physically motivated magnitude scale. Actually, for long, in my view, today we simply don't have reasonable magnitude scale for long period earthquakes because we don't know what is the source process. Okay, because if it's a moment, it's one thing. If it's a force, it's another thing. And this is something that we should develop apart calibrating them. And then based on this, we eventually should develop all scaling laws to have reasonable interpretation and not to consider every source as a completely individual case. Okay, and here, so now what are the reasons for this difference between simplicity of tectonic earthquakes description and unknown description of volcanic earthquakes? Obvious reason is complexity of volcanic systems. They are more complex. There are more things are going on. But I think there is today another very important reason for this delay in volcano seismology is the organization of volcanic observations. It is very fragmented. Okay, so what I mean by this, is that if we compare what is going today in earthquake seismology, we have very good situation with most of data worldwide in open access and existence of international monitoring system that monitor earthquakes with a set of uniform verified methodology. Volcanoes are monitored and studied mainly by volcano observatories. Okay, so the data, unfortunately, up to date I'm not speaking in this case about IPGP observatories, but about all other observatories, often remain within observatories. Actually, IPGP observatories, they release their data very nicely. Okay, and then because this monitoring is isolated and fragmented, also there is no uniformity of methods. Okay, and this is also obviously stops advancing the science. Okay, so how this should be changed? So again, the current situation is that every individual volcano or volcanic region is nearly exclusively observed, monitored by its own observatory. And there are obvious disadvantages with this. So every group only study some sample of the global data set. Imagine, for example, for earthquakes, if seismologists in California were studying only Californian earthquakes, and seismologists, say, in Turkey were only studying earthquakes in Anatolian faults. I think they maybe never would end up with universal scaling laws. They would still characterize some particular cases. And this is our situation today in volcanic seismology. Then, obviously, every volcanic observatory is small. There is a shortage of staff, resources, and also absence of all necessary skills. So this is, if we want to advance, we need to do at least one thing, to push forward sharing the data. I think the situation with seismo-volcanic data and volcano observation data today is, I would say, completely outdated. I think this should not be tolerated too long. We need somehow to push forward volcanology community to share the data openly with all scientific community. And again, IPGP observatories are today in the forefront of this. Okay, but in addition to this, I think we could rethink the way about how we study and monitor volcano. Again, this idea, one volcano, one observatory, is not efficient. And in comparing with earthquake monitoring, we have seen that large centralized monitoring centers are more efficient for uniform monitoring for advanced science for many reasons. So we may think about creating centers that study volcanic data not only in place, but also some remote centers that study simultaneously many volcanoes, and this will allow advancing many things that are indicated here. This will provide global view of data and source processes. This will get easy access to necessary computational resources. Again, this will uniformize the methods, and also this will allow implementation of more recent technologies that we need, like network-based methods and things like machine learning and so on. So I stop here. So here are my conclusions. So my main conclusion is maybe still the same, that in my view, volcanoseismology is a part of seismology that we still have some first-order unsolved problem, which makes it a really exciting area where discoveries are still possible. Thank you.
Okay, thank you, Nikolai, for this talk. Questions, comments, remarks? Who wants to be the first one? Okay.
Thank you, Nikolai, for your nice talk. I was a little puzzled by the fact that you mentioned that there aren't really like source models for understanding volcanic earthquakes, but for example, there are studies by Bernard Chouet in the mid-80s, and he has made some source models. So I wonder if the source models are probably not correct, but there are still physical ways to understand these seismic signals. So why aren't they used more?
Yeah, you're right. There are works by Bernard Chouet and others. Yeah. Actually, there are many source models for volcanic earthquakes. And some of them were validated with some particular cases of observations. But what I would like to see as a source model is some more universal paradigm. So because today, Bernard Chouet, for example, his fluid field fracture model has been applied on a few volcanoes, but still only validated with maybe a few hundreds of seismograms. nobody really checked how universal is this model, how we can simply use it to quickly interpret the observation. For example, very basic question, can we use this model to develop magnitude scale? There is no answer for this. Yeah. And to efficiently interpret many observations, we need not just many models that describe some particular case, we need some more universal paradigm that would allow us to make some simple measurements and to immediately, or more or less immediately, get some simple inferences, even in a statistical sense.
Somebody else?
Yeah, you mentioned that the zone around the Moho is very important for volcanoes and for volcanic zones. For volcanoes, did you try to image this deep magmatic reservoir? Is there a way to have some sharp images of this zone?
Not me, but other people tried. And up to date, I know two approaches that were tried. Tomography. Tomography, I think the results of volcano tomography are, I would say, mitigated for this part because on volcanoes where you don't have this deep seismicity, you will not have rays that go through this zone and you will not image it. On the volcano like Kluchevskoy, where there are a lot of seismicity in this reservoir, you will image something, but your final tomographic images are obviously biased by the distribution of your seismicity. So tomographic imaging is, especially with the resolution that we would like to get, is very challenging. Another approach that has been used is based on receiver function, okay? And in my view, this was more successful because even if this did not give us very clear, nice images, this allowed to compare S minus P travel times measured in receiver functions and from earthquakes. And for example, for the Kluchevskoy volcano, this allowed to show that most of these deep earthquakes are occurring below the Moho. Okay, so this is my answer. But obviously, any suggestions about to advance this would be welcome.
Thank you, Nikolai. You talked about different type of volcanoes which are of the basaltic origin or arc origin. The rheology plays key role in the earthquake source mechanism or the fault mechanism. On the arc mechanism, you have very different rheology, and if you come to the ridge type, which is the Iceland, very different, where you know the rheology very clearly, you know the processes. So why don't you go to Iceland and understand this process where things are simpler than going to Kamchatka, which is very, very complex. You have both everything, arc versus mantle volcanism.
First of all, the statement that basaltic volcanic systems are simpler, I mean, one would agree, one not, but okay. Then I work in Kamchatka for two reasons. First of all, I personally like Kamchatka, but then most importantly, I can get easily access to the data from there. I don't have close colleagues in Iceland, so
it's not only you, I mean, it was the process I was referring to. I'm not referring to you as a person. Looking at the process, generic process,
no, yeah, yes,
easier
but
to address in Iceland, where you have a rheology is clear, we know magma is coming, all the things are very well constrained in terms of the physics of melting, physics of the melt movement, and the earthquakes.
But I just was finishing my answer. I would like to study Iceland if I could get the data in open access. I cannot. So and most of seismologists are facing this barrier. So this is what happens with volcano seismology. So I can easily get data from Cascadia, from Japan, not from Iceland, not from Italy. If I want to study volcanoes, most of data are protected. And this is what should be. Do you see what I'm saying? Yeah.
More questions? Two. One here and then I come up.
Thank you, Nikolai. I'm very surprised for the lack of seismicity in Kamchatka being in between the upper crust shallow volcano and the Moho. You really checked that there was nothing really happening, no migration of little events, which could fit your model of upward propagating pressure pulse?
It's not that it's completely absent. I am going back to the figure initial. Yeah. You can see in the catalog there is some seismicity. Yeah. Okay, but there much less of it if you look statistically. So when with this much less intense seismicity, it's much more difficult to get inferences about possible migrations. Actually, at this moment, there is a master project where we try to better detect this earthquake again based on this template matching and so on. Maybe we will find some migrations, but I don't know.
Okay, and the related question is, well, if you have this pressure migrating upwards with little seismicity, at least you might expect some geodetic deformation from GPS or tiltmeter or strainmeters. Do you have such instruments there, and what do you see?
No. Unfortunately, on this volcanic system, there is no GPS located close on volcanoes. And
are there any plans to put geodesy in addition to seismology, as you put in the introduction?
Unfortunately, not immediately. Okay, but this would be obviously nice. Okay.
Yes, so you showed that there are a lot of deep LP events in Kamchatka, and of course it's a very interesting result. But in fact, when you see the seismic activity on other volcanoes, there are few examples with so deep LP activity. And so why? So is it because a problem of geometry of the seismic networks? Is it a problem of techniques for locating these events? Or is it a problem of volcanic processes? What is your opinion about this?
I'm absolutely certain that this is a reality. In this place, there are really a lot of these earthquakes. You just see them on seismograms without any special. Let me just show this. Yeah, for example, this event.
I have no doubt on the reality, but I am wondering why on other volcanoes people are not detecting this.
Why there are less of them on other volcanoes? Maybe because the level of activity on most of other volcanoes is less intensive than here. I don't know, but I think at least a few people tried to locate these earthquakes with special dedication, and they didn't find as many as here. But actually, there were recent papers showing that these phenomena exist in places where before people didn't report it. So I think maybe with better detection, this will become something more systematic. I don't know. Again, to answer this, this would be nice to have easy access to data from different volcanoes. For example, we developed this detection procedure. We could easily implement it, but getting the data, you know, it's very difficult.
Okay. Any other question? If not, maybe we could thank the speaker once again and meet in the
Thank you.
session.